manufacturers, PCBs, catering mainly to the prototyping industry, but also up to small and medium scale batch runs. I've used them for projects in the past and for this project, and I can thoroughly recommend them based on quality, and this is, I should say, absolutely nothing to do with the fact that they gave us free stuff, although there may be some correlation. With regard to the primary mission, that is measuring temperature and pressure, for the pressure we decided to use a Mesh-Spec MS5637, they're Swiss-made, so it can be guaranteed accuracy more or less. And this, in fact, if you use the full resolution of the data, you can obtain an altitude reading according to their marketing material of, with a resolution down to 30 centimetres. It's digital, it's very compact, in fact, although it may appear as if it's about 30 centimetres across on the wall, it is actually a very small surface mount chip, and the reason why we chose this one in particular was because it has only 4 pins. It has only the I2C pins and the power lines, which means it's very much easier to solder down than, for instance, the MPL 311582. I don't know if you've heard of it. Another common pressure and temperature chip, which is 8 pins, and so you have to prevent shorts between all of these 8 pins, which is much harder when you're soldering it by hand. This also measures temperature, and that allowed us to get an on-board temperature reading. To get a temperature reading of the air itself, which we felt might be what you were interested in, we had a second temperature sensor. This is a hygrometer, actually, the IST HYT271, another Swiss-made component, in fact. And this measures temperature and humidity. It is a reliable chip for the latter, which is somewhat rare. It's also factory calibrated and very compact. If we have a look at the graphs we obtained from these data, you can see on the top graph internal and external temperature. The blue line on the top is the internal temperature, as you might imagine, and you can see that there is quite a nice correlation between the internal and external temperatures. You can also see the rate, there is some smoothing in the top line because it was more deeply integrated with the electronics. You can see the little bumps just to the left at about 1,000 seconds in, if you look at the x-axis of time read these graphs. Those, we believe, were where the CanSat was put into the into the launch tube itself. And then, interestingly, you can see a reasonably flat section for the entirety of descent, which we believe was because all of the sensors were shielded by the launch tube assembly. Then, if we just skip to pressure for a moment, you can see a nice gradual decrease, which is much what one would expect with an increase in altitude, until suddenly at about t equals 1800, you have a very rapid descent. This, in fact, was possibly too rapid. If we have a look at the top graph, you can see the sudden drop in temperature as the components are once again exposed to the outside air, and they have their cooling air flowing through them. And then, especially with the top blue line, you can see a gradual increase once again as the electronics start to warm things back up. On the bottom, we have a pressure drop, much as one would expect, and since, as we will come on to in a few minutes, the parachute unfortunately failed to deploy correctly, this was an especially rapid descent. In fact, I don't have an altitude time graph in this presentation, but I plotted one, and according to my calculations, it was descending at much nearer 20 meters per second than 10 before it hit the ground, which was, shall we say, not ideal.
Our singular objective was a rover, which, as you can see, this early prototype worked fantastically and could overcome all sorts of stationary obstacles.
Almost managed carpet.
So the idea with the rover was it would be a radio communicating rover. It would be able to navigate autonomously to WGS84 coordinates or OS grid references, and it would relay all sorts of data back to the ground station, including temperature, pressure, and humidity. On the note of humidity,
indeed. Now you may recall that earlier I mentioned humidity. In fact, we measured that using the external temperature sensor chip, which I mentioned earlier, and the objectives with this were to calculate and investigate the dew point, that is, the temperature at which water condenses out of a given out of the sample of air at a constant pressure. Now, we wanted to investigate specifically how this changes when measured at different altitudes for two main reasons. It's very important for calculating the probability of asthma attacks, and more interestingly, for predicting carburetor icing in light aircraft. So, the if we plot a graph of humidity versus temperature, relative humidity versus temperature, we have what looks initially like a complete mess. However, don't despair, because if you look, you can see a purple trend line fitted to it, and in fact that's quite a neat line, and exactly what one would expect. Because as one increases the temperature, the capacity of the air to hold water increases. The relative humidity is calculated as the partial pressure of water vapour in the air over the amount of water over the total potential partial pressure of the air. So if the water volume remains roughly constant, that's what one would expect. The wild fluctuations you can see there are because obviously these readings would have been taken at different altitudes and at different pressure levels. So that I felt was quite satisfactory data.
Moving on to the electronics, I'm going to hand you over to our head of electronics.
Thank you. We had, for this project, since we had a number of different logic levels running on the board, we had two separate power supplies, 3.3 volts and 5 volts. We're running off a lithium polymer battery, which has a nominal voltage of 3.7 volts, so obviously 5 volts is a bit difficult. We used a boost converter, which simply ups the voltage of the motors, and a low dropout regulator to power the microcontroller itself. We considered using a switching regulator, which might have been more efficient, but because we weren't worried about power consumption too much, it was not a great concern. This provides a nice stable power supply, which is good when you come to our next section, which is the microcontroller. You can see on the left there the TC 3.1, which is the board we used. It is an ARM-based microprocessor board, and it is, as the name suggests, very small. It comes with all of the programming circuitry on it. In other words, you can program it over micro USB and you can get data back from it over micro USB. And that is invaluable if you don't want to have to use JTAG programs and so on, which you would if you had a standalone ARM chip. Finally, the radio modules, which you can see on the motor driver, sorry, which you can see on the right there, was the DRB8833 PWP, as mentioned in the report, which is an HP driver and a very small surface mount package. And the radio modules, which I feel do deserve a word, were quite astonishing, actually. This is a graph of the signal-to-noise ratio over time, and over altitude. Altitude increases in the x-axis, and as you can see, signal-to-noise ratio remains almost exactly the same. And to this end, in fact, we tested these radio modules over a distance of more than 1.5 kilometres open space using the ERD antenna, and we saw almost no degradation of the signal quality. This was the base station software, which I knocked up for it, and this is written in PyGTK. It's a GTK framework, which is a common cross-platform graphical interface framework, and we will have a little demonstration of that later. But as you can see, on the left, it's split into 3 columns. On the left, you have data statistics and the raw serial data coming in. In the centre, you have on the top the process data, and on the bottom, a command panel. And the right section is all command panels. Parachute release, strut release, and the rover functionality, which I think we should cut out fairly shortly. But first, a little diversion on the excellent parachute.
The parachute, which was calculated by another team member who couldn't be here today, we established that for a terminal velocity of 10.4 meters per second, all we need is a parachute of 50 centimeters in diameter. Unfortunately enough, it appears our parachute don't have sufficient depth or enough of a dome in order to slow down the descent, so we end up travelling at about 50 meters per second, was, I believe, the calculated value.
Sorry, just to correct that, 15 or 20
meters a second. That 50 meters a second proved a problem for the rover itself, but we've established the problem, and we can redesign the parachute to have much more of a pronounced and deeper dome.
Right, this is my section. The chassis prototype. This was one of my first designs. As you can see, it implemented plywood ribs and rubber wheels. Now, the motors would be mounted directly into the engine, so that, well, I'm sure we'll come on to that later, but at any rate, it used copper rods and integrated all the electronics on the inside. However, during testing, as you saw, the problem was it would get caught. So we realised we had to increase clearance. Now, we made some minor changes, and what we did was basically cut off half on the inside. We also changed the wheels, again, section. We mounted an aluminium dome onto an aluminium plate with a strut release system bolted on the bottom, as well as the motors stuck on the arrowlight and then reinforced with more aluminium. The whole idea of this was increased clearance so it could tackle grass and inclines, which was a problem previously. We also realised at this point that the weight restriction, our final design weighed under 250 grams, so we realised the weight restriction wasn't really going to hinder us all that much, so I decided to make it a 2 mil thick aluminium plate, just in case, as happened, the parachute didn't work. It suffered fine. It was basically unscarred, which is great.
And in order to meet that specification, we ended up, in fact, having to put quite a significant quantity of lead shot into a bag attached, in fact, to the parachute, well, not to the parachute itself, but to the cord running from the parachute, which allowed us to increase the mass of the CanSat to meet the specification almost exactly without compromising the design or space in the CanSat itself.
On the note of the parachute release system, in order to avoid the parachute getting entangled in the wheels of the rover, we had a linear servo motor controlling a pin release system for the parachute, so that upon command it could release the parachute and therefore the rover could drive away unhindered. This worked perfectly on the day, and the parachute landed clear of the rover, and the rover was able to move independently.
The wheels, yes, this was my wheel prototype. I was going to use rubber on the basis that with the chassis being of a 64mm diameter and the wheels are 66, on impact the rubber would compress slightly to allow more of the chassis to stay the pressure if it landed flatter on that angle. However, it didn't work, was the problem. We couldn't key it properly because the motors are keyed in a D shape and the rubber just wouldn't hold it. So the rubber would hold as the motors spun, essentially screwing our design. So instead we changed to acrylic wheels, which hold the key perfectly, and added foam on the sides because to add grip on grass and inclines. It also didn't add too much weight. As you can see on that picture, we do have the strut mechanism in the very right-hand corner of the wheel. This was inbuilt into the bottom of the aluminium frame, so the strut could be released using a spring perfectly on time with the spinning of the wheels. This was to balance it as it moved, because as you saw in the program, one of the major problems was the middle would spin and the wheels would just keep going back and forth, eventually overcoming it without any direction. I think that's my bit done.
Now I think we move on to Hugo for a bit of reaching out, hopefully not overreaching.
As the team's outreach program, we gave a series of talks, one to the School Engineering Society, NSOC, and the SBS Space. The project was also presented to parents visiting the school on the school's open days. As part of an internet-connected campaign, which is important in this internet-connected world, we had a website, teamimpol.se, which included a regularly updated blog with the technical changes we've been making. We also had a YouTube channel where videos, including those in this presentation, have been uploaded, and a Twitter feed, which not only provided technical information, but also amusing anecdotes that were overheard over the course of the trip. So, we'd like to thank Drs. Patterson and Dr. Weller, who accompanied us on this trip, as well as the ESRO, the University of York, and the National STEM Centre. I think our trip could best be summed up by a limerick. So it talks out a team, most reliable, whose data were well quantifiable. They worked all through the night, to the judge's delight. Their skill and resolve undeniable.
Well, that's absolute rubbish. I feel it could be better reflected through a separate anecdote. St. Paul's had a team so atrocious. Their attention was rarely on focus. The tasks they were set, they were quick to forget, instead making rhymes most precocious.
I feel we struck a middle ground.
Yes, I think so. And on this note, actually, just before we invite questions, I would be very grateful if you would permit me to make a little demonstration of the rover itself, which we have here, and we can allow the switch that on. And now, of course, we just have to hope that it works on this occasion. Although we have, I have to say, found it to be reasonably reliable. On launch, we had the rather unfortunate issue that one of the wheels snapped on. In fact, not only it wasn't the wheel that was at fault, but in fact the motor itself sheared clean off, which was, well, a setback, one could say.
I feel I should mention that in testing this didn't happen at all, but there may be several reasons, including the parachute deployed, and we were testing from a much lower height. Now, it wasn't actually my fault, thank you. It was the motor itself that actually sheared, so we hadn't tested that on the 3D modelling system. We had actually, well, I had made the mistake of simulating it as a solid block of steel, which didn't snap. In reality, not so solid. we can test it now and hopefully show off.
On the note of the parachute testing, we also did use the tube deployment system, which may well have tangled up the parachute, and that could have been another error because it didn't fully expand, was another one we encountered. And on the note of its reliability, despite the fact that this motor sheared and the central shaft actually broke, the two halves that survived were completely intact, the electronics all worked perfectly, and the majority of the gears were still inside the motor.
And in fact, on the subject of mission criteria, if you look at our primary mission criteria, we fulfilled all of those, and in fact on the secondary mission criteria, despite the fact that the rover was not successful, 4 out of 7 of the secondary mission criteria were fulfilled, namely the telecommand aspect, the investigation of dew point and the relaying of humidity back to the base station, and the there is a fourth one. What is it? Indeed, there was the telecommand and the humidity measurement. Also, the successful release of the parachute. So now, in fact, I think we are ready to demonstrate this. Please excuse me for not demonstrating the strut release mechanism, because since I only reattached the motor, I've only reattached a new motor rather tenuously. I don't want to place any additional strain upon the system at the moment. But if we send that a command to begin moving, off she goes, and there we are now. There is a certain amount of latency in the command system, I have to confess, but I think this is a good thing, because if one was to learn to drive on a Teen Impulse CanSat project, you have to think ahead quite some way in order to get it to perambulate around your table, just like this. And on that happy note, I would like to thank you for listening to us drone on and on and on, and invite a few questions. Thank you.
So I was wondering, could you please tell me why the microcontroller was changed from, what was the considerations you took into account, why you changed the decision what to use the C-lines?
I think that's probably best to see. The electronics had to be very compact, and the T-minus board, although the system integrated within very solidly built, unfortunately, if you look at the size of the CanSat, all of the electronics fit inside this top portion. The T-minus board would in fact have been about the size of the wheels, which would have reduced the ground clearance quite significantly. Also, this has a very fast ARM processor on it. In fact, it's overclocked to 96 megahertz. It has 64 kilobytes of RAM, which is useful for a program which deals with a number of different interfaces, SPI, I2C, and serial interfaces, the GPS, the radios, and the other component on the board, the pressure and temperature sensor, for instance.
Sorry.
I conducted, there's another one for me, I'm afraid, sorry, I conducted a test on the rover in which I ran both wheels at full speed ahead for more than 3 hours. I had the radio transmitting packets twice a second, and during that test with the lithium battery that we are using, the battery voltage decreased from the fully charged 4.3 volts to 3.73 volts, which is still above the nominal voltage of the battery. Based on this, we decided the specification which stated that the battery, that it had to be able to be left on for 3 hours before voltage was more than adequately met.
How far do you think it can go?
How far? Well, I think it, provided that it had reasonable traction. I don't really know, because I suspect it would make quite a good distance before it ran out of power. I'm not entirely convinced that that would be the issue. I think it would be more a question of whether it encountered any obstructions which were significantly larger than itself. Because obviously, in an airfield environment, there is the occasional, for instance, a large mound of gravel. Not that anyone would need that lying around in the airfield, but
On a perfectly flat plane, the physical components were all strong enough to continue running as long as the batteries lasted. So it had good reliability.
The most recent design could also do inclines, which the previous one couldn't. And more importantly, when it came across a small ditch or something, instead of getting caught and essentially spinning around itself, the strut would eventually push it out and hopefully go in the same direction, which is quite important for steering it, basically.
unfortunately, we didn't get, during the launch itself, we didn't get a GPS fix. I think several other teams have suffered the same problem there. We had one perfectly well during testing. We had which meant unfortunately we were unable to test the autonomous navigation aspect of the software.
Although the motor shearing in half would have
There was that as well. But we were able on the launch site to demonstrate, during the parachute drop, the telecommand release and the parachute release functionality worked correctly, so that's an example of telecommand working successfully. Also, we were still able to command the motors after it landed. There was no damage to the electronics of the CanSat during the landing, despite the rather higher impact speeds anticipated, and so that, I think, was reasonably successful. I am not entirely certain, but I rather suspect it may be, since we have packed everything into this cam shape, we may have, it may well be that that the aluminium involved creates various reflections of the microwave frequencies involved, which could cause issues. Alternatively, it may seem to be conducting away the maybe very low level GPS signal. I suspect, though, that since we had it working during testing a few days ago, the issue came, in fact, on Sunday, where we had a microcontroller fail on us, and that was due to a current planted on the linear servo, which I've since rectified with a 1K protective resistor. But that took out the microcontroller and meant that I had to desolder everything on that side of the board and replace it, which obviously not only pushed the deadlines right forwards and made it meant that we were working until fairly late on the day of launch, but also resulted in I suspect, meant that instead of mounting the aluminium plate as we hoped, the electronics were a bit bulkier, and so